Good evening, Hannah, and welcome back again. The Unit 5 Stochastic Process and Markov Chains. The same syllabus will be there for CYSM and MSF. Now, first we'll see that what is that stochastic process and all. Now, we need that connect with that the history, applications, and properties. What are the definitions will be there? What's the concept behind that? Why we are studying all those things we'll see now, right? And let me first start with that many real world problem applications of probability theory have a particular feature that the data are collected sequentially in time. The few examples are weather data, stock market indices and air pollution data, demographic data and political tracking polls. So these also have in a common that successive observations are typically not independent, but we refer to in such a collection of observations as a stochastic process. Now, formally, stochastic process is the collection of random variables. Mathematically, stochastic process is a set of random variables. We can take that set xn x of t and which small of t belongs to the capital T that takes that values in a set as that state space, and there are also known as a random process or random functions, right? The collection is indexed by set T, right, which is known as the indexed set. And then two most common index sets are natural numbers, say T is equals to 0, 1, 2, 3, and non-negative real numbers also we are going to take that 0 and infinite, which is visually represented discrete time and continuous time respectively. Next, going to the in-depth of the thing of the definitions now. First, we can say that the first index set that gives a sequence of random variables or x1, x2, all those things, right? So it takes that all these random variables, and the second collection of random variables is x of t and t is greater than or equals to 0. One random variable for each time. The state space can be a finite or countably infinite also, or uncountable also, depending on the application. Then state space. What's the state space? The values assumed by random variable are called states. Set of all possible values of individual random variable xn of stochastic process, so which is n greater than or equals to 1 is known as a state space. Now it is denoted by the 1. The state space is said to be discrete if it contains a finite countable infinite points also will be there, otherwise it is called that the continuous. Then x of t is equals to max or min temperature during the interval time 0 to t. And for the example, we can see that a queuing system. In this system, the number of persons joining in the queue, the number of persons being served at the time interval t, the number of persons in the queue at the time are all random variables depending on the parameter t. And the second example, the turbulent fluid flow. In turbulent fluid flow, the velocity components of the fluid are random variables depending on the space coordinates x, y, z, and also with the time t. Now, Gamler-Roon problem. Suppose this you already know about that. Many movie people also always are showing that the Gamler-Roon problems in abroad, which is very popular in abroad, not in our country. We can say that the glance about that. Suppose the Daimler wins or loses a unit with a rupee or dollar with the probabilities P and Q respectively. Let the initial capital be Z and his component initial capital also we are going to take that the A minus Z, and that the combined capital is A. The game continues until the gambler capital is reduced to 0 and increased to A. That is, one of the player is ruined. We can understand that capital of the gambler after n stages is a random variable. Okay, Markov process and Markov chain. This is very important in stochastic process. Let me go to that one by one. These are all the x0, x1, x2 be a sequence of discrete random variables taking the values some set S and that such that we are taking that P of xn plus 1 equals to j, and these are all the variables starting with that I0 to in minus 1, and simply we can call it as x of probability of xn plus 1 is equals to j of xn equals to j. For all I, j, k dash dash all will be there in the set. And the sequence xn is also is called Markov chain. Depending on the property is called Markov property. This defining property, which can do states in words like a future demands only upon the present, not upon the past. In other words, the occurrence of the future state depends only on it's immediately preceding the status. So these very very important for understanding the Markov process and Markov chain. N step transition probability, Nana. This is applicable for n step, like power, like n, say matrix A will be there, no, n step, no, A square, A cube, like that. The n step transition probability is the conditional probability that the system will be in a state J after exactly n steps, given that it starts in a state and I at any time t that is given by, so this equation will get it. If n is equals to 1, and we'll get that the P of Ij equals to P of Ij. Then n step transition probability satisfies the following two properties. P of Ij is greater than or equals to 0, and then this is equals to 1. These two are the axioms. Okay, the same thing here also, because Pij is nothing but the transition probability matrix. No, that's the we are taking here. Now, the Markov chains are considered to be in this chapter the following properties: a finite number of states and the stationary probability, transition probability star. Now, in the first we are seeing the transition matrix. The transition probabilities can be arranged in a matrix from such a matrix whose elements are non-negative and sum of all the elements should be 1. This is mandatory and said to be transition matrix or one step transition probability matrix. The matrix, transition probability matrix, will be like this. So this is a 4 by 4 matrix, and the states will be 0 to 3. States will be 0 to 3. So it is looking like this. And now transition matrix will be the list all the states here, Nana, and then here also list all the states. That's what we are going to see that. And then next one, and then insert a probabilities here. Every row should be 1. Every row should be 1. In the transition probability matrix, the row represent now from xt, the columns represent next and 2 xn plus 1 or xt plus 1. The entry ij is the conditional probability of going from a state to other state j, I to j indirectly. Now, diagrammatic representation of transition probabilities. Okay, the transition probabilities also can be represented by two types of diagrams. Transition diagram is the one. Transition diagram shows that the transition probabilities are shifts that can occur in any particular situation. Each state is represented by the nodes, and the arrow from each node to some other nodes indicate that a possible state to which the process can move from given state. So this is the graph, and we are based on that we are going to write that the matrix, transition probability matrix. We can see that how many states are there: E1, E2, E3. Now E1 to E2 is there. The path. Yes, E1 to E2. So there only you are going to keep that 1. So E1 to E3 is there, no, 0. And E1 to E1 is there, no, 0. So 0 only we mentioned. Now we calculate that each row has to get that 1, like that, based on the graph. Now you are going to see that E2 to E1, E2 to E2, E2 to E3. Now if you add that these two, you need to get that 1. If you add that these two, you need to get that 1 based on this. So then only we can take that the transition probability matrix for getting into that here Markov process and Markov chains. A zero element in the above matrix indicates that transition is not possible. If it is 0 will be there, transition is not possible. If some value will be there, yes, it is possible. Now, n-step transition matrix. Now, matrix. Okay. Now, the n-step transition matrix, which is called as a power n or p power n, can be obtained by computing the nth power of the one-step transition matrix, right? So, p into p. Suppose p cube is there, no, p square, no, p into p, like that. Okay. Now again the same with the help of the gambler ruining problem only, not the concept. We are taking that some problem. Another example gives that gambling. Suppose that a player has a dollar one. With each player of the games wins that dollar, and the probability here p of greater than 0 or loses that the dollar with the probability of 1 minus p. Nothing will be there. That is p, then 1 minus p. The game ends when the player either accumulates that dollar 3 or goes broke. Okay, write the transition matrix we need to based on this data. The game in Markov chain in the state representing player with the current holding of money is a 0, $1, $2, or $3. With the transition matrix is given by like this. Okay. If you see that, you need to get that all the things should be 1. Otherwise, we can't calculate using these states. Now I have given that example. Only one item is served in a day. This is the previous. I think I didn't keep that, but anyway, you can see that based on the pictures also. Okay, only one item is served in a day. One item cannot be served in a 2 consecutive days. So this is the problem indicates, right? Now where it is going to applicable in the hotel, right? Now we can see that taking that here a circle, I mean ellipse, I mean not, don't take into that the circle, ellipse and all. Here we are discussing with the stats. No, now you can see that suppose this is a burger and this is the pizza, and like that we can take that this is the cake, like that. Okay, now p of x1 one item, p of first item and the second item, and then next third item. Now suppose you want to add that up, p of 4 and equals to that, I mean that p of 3, p of 3 and then next x1. Okay, now you can see that p of x4 will be getting like this. Okay, now same, one item is served a day, item cannot be served 2 consecutive days, right? So based on that, now we are going to take that, because we need to get that whatever you want to do that. Suppose PHB, that means a pizza, and then next a burger, and then next a cake or something, whatever you right? And then P to P is there, no, P to P is there, P. Can I put that here? P, say this is H, this is burger. Okay, now P to P is there, no, 0, you kept that, right? And then next P to H will be there, yes, it's there, 0.7. And then next చూడండి, what is the value? 0.7. And that H to B is there, yes, it's there, right? And then you need to write that 0.3. Okay, so like that you have to sorry, this side, like that we need to get that each row should has to get that 1 1 1 1 1 1. Okay, so based on this data. Okay, now which of the following matrices are stochastic? A, you add it, yes, this is the stochastic matrix, but so which is not a square matrix, so that's the reason which is not a stochastic. Yes, it's there because adding 1 1 1, but this is square matrix. Now 1 and this is not, no, and this yes, and this is not, because negative sign will be there here, negative sign. Okay, like that. Now tennis game at reduce based on this picture. This is a homework for you based on this diagram, transition diagram. Now you are going to find out that this transition probability matrix. So this is also Professor Simon's, I think I explained in the class also, nothing to worry. Walk and bicycle only, you can do that. This is also homework. Okay. Now come to that next one, first and higher order Markov process. The first order of Markov process is based on the following 3 assumptions. The first one is finite, and the second one is that next outcome depends on only the preceding outcome. Okay, and the transition probabilities are constant but over time. And the second order is Markov process assumes the probability of next outcome. Main outcome is nothing but here state, maybe depend on 2 previous outcomes. Likewise, the third Markov process assumes the probability of the next outcomes can be calculated obtaining that the taking of the of all the outcomes of the past 3 outcomes. So these two are very important, Nana. This is 1 and this is 2. Okay. Now the Markov chains are of 2 types, ergodic and regular. Ergodic Markov chain has nothing but it is possible to pass from one state to another state in a finite number of states regardless of the present. That's what I previous also telling about that. A special type of ergodic Markov chain is a regular Markov chain, right? Next, a regular Markov chain is defined as a chain having transition matrix such that for some cover of P, it has only the non-zero positive probability values will be there. Thus, regular chains must be ergodic chains. And the easiest way to check that if ergodic chain is regular to continuing that squaring that the transition matrix until all zeros should be removed. Otherwise, you can't take that that ergodic. Next, state probability vector, steady state equilibrium condition. State probability, it is the probability that the system is being in a state I at a time t is equals to n. It is denoted with that p of I n. Suppose a 0 you can take that, and then next 2 also you can take that, 3 also you can do that. Means steps, n steps. Probability vector, it is a row vector representing the state probabilities of all the states at a time t is equals to n, and it is denoted by with the r of n. R of n is equals to p1 of n, p2 of n, p3 r. Now here 1, 2, 3 are the states available in the system. Next, the system of equations can be written in the matrix form r of n plus 1 is equals to r of n into p. This is called the transition probability matrix. For r of n plus 1 is the row vector of the state probabilities at a time n plus 1. R of n is the row vector of the state probabilities at a time t is equals to 1, where p is called the matrix of transition probabilities. The state probabilities at t is equals to 0 known. These can be found by using this formula. First 0, r of 1 will get it. And n equals to 0, no, you will get that this. If n is equals to 1, no, you will get like this. If n is equals to 2, you will get that like that. So dash dash dash. It's a n step transition probability matrix. Now, whatever we discussed, no, so the same, all the things will be calculated using that this formula, Nana. Using this formula, this is the homework for you. I kept that how to get that all the transition, power of the matrices. You can do that. Next, this is also the same. Simon, previous slides also we have seen that the same thing with extension long run. Nothing is there here. Okay, same formula, Nana. This formula. Okay. Next, when this happens, we can say that system is steady state or a state of equilibrium. In this situation, all vectors are equal. All vectors are equal. Now we can call this vector is called fixed probability vector or equilibrium vector. In the above problem, previous problem, we have seen that now 1 by 3, 2 by 3. If you add it, what you are going to get that 1 no, right? And here the formula will be r of k into p power n equals to r for large values. Otherwise, r of n tends to r, and as n tends to infinite for large values only it applicable. If the equilibrium vector r is multiplied with the original matrix, then the resultant equilibrium vector you will get that rp is equals to r, like the xp equals to x, vp equals to v, like that. Next, classification of states and chains. We can say the state J is accessible from state I. We can written as I to J. Now this power of the matrix will be like this. Next, two states I and J are said to be communicate when again same when it is can be written as I to J. If they are accessible from each other, then we can say I to J means I to J or J to I, both vice versa. Then the graph will be like this. Periodicity. Periodicity is nothing but return state is defined as the greatest GCD of all M such that the transition matrix will be always greater than 0. And this follows that the GCD will be DI like this. A state I said to be periodic with a period DI. DI is always greater than 1. A periodic DI equals to 1. Okay. Next. That's it. I think I repeated the second time also. So hope everyone understood that this stochastic process with Markov chains and all in MSF as well as the COSM class. Thank you. Thank you.